Chapter 6, Module 4. In a previous module, we have discussed several properties of exponential map. We have discussed something called path lifting property of the exponential map and homotopy lifting property of exponential map. We also defined the degree of a loop using this path lifting property of the exponential map. In what follows, we are going to define a function from the collection of equivalence classes of loops of S1 to the integers, assigning the degree of a loop to the corresponding equivalence class. In what follows, we shall show that this particular map, which we call degree map, is an isomorphism. We quickly recapitulate the definition of degree of a loop. For any loop alpha in S1 based at 1, the unique integer alpha cap 1 is called the degree of alpha, denoted by deg alpha, which we shall say that it is degree of alpha, where alpha cap is the lift of alpha with the property alpha cap 0 is equal to 0. We state a theorem that if alpha and beta are two equivalent loops in S1 based at P0, where P0 is the complex number 1, then degree of alpha and degree of beta are equal. Now we prove it that given that alpha and beta are two equivalent loops in S1, so there exists a homotopy capital F from I cross I to S1, where I means the closed interval 0, 1, such that if S0 is alpha S, if S1 is beta S, F0t and F1t for all values of t is equal to P0. By homotopy lifting property of the exponential map, there exists a continuous function f tilde such that f tilde 0, 0 is 0 and exponential composed f tilde is equal to f. We define alpha tilde by alpha tilde s equal to f tilde s0 and beta tilde by beta tilde s equal to f tilde s1. Then clearly alpha tilde and beta tilde are continuous maps. Also, for all values of t, exponential composed beta tilde evaluated at any point t is equal to exponential evaluated at f tilde of t1, because we have defined beta tilde in terms of f tilde, and that is equal to exponential composed f tilde of t1, which is equal to ft1. And from the homotopy we know that ft1 is equal to beta t. Similarly, we have exponential composed alpha tilde will come out to be equal to alpha t. Hence, exponential composed beta tilde is beta, while exponential composed alpha tilde is alpha. Also, beta tilde 0 is f tilde 0 1 and alpha tilde 0 is f tilde 0 0. Now, we know that I is connected, that is closed interval 0 1 is connected, and a singleton set is of course connected. So, 0 cross I is a connected subset of R cross R, thereby giving the continuous image f tilde 0 cross I a connected subset. As the set of integers with respect to the induced topology from R is totally disconnected, f tilde 0 cross I is a singleton set. Hence, in particular, f tilde 0 0 is equal to f tilde 0 1, and it is known that f tilde 0 0 is 0. So, we have beta tilde 0, which is f tilde 0 1 is equal to 0, and that is equal to f tilde 0 0, which equals alpha tilde 0. Therefore, beta tilde is a lift of beta and alpha tilde is a lift of alpha. Hence, by definition of degree, degree beta is beta tilde 1, which is f tilde 1 1. On the other hand, degree alpha, which is alpha tilde 1, equals f tilde 1 0. By a similar argument, as singleton 1 cross I is connected and f tilde is continuous, its continuous image, that is f tilde 1 cross I, must be a singleton subset of the integers. Thus, degree alpha, which is alpha tilde 1, has the value f tilde 1 0, which shares the same value with f tilde 1 1, which is equal to beta tilde 1, that is the degree of beta. Now, we state another theorem with the help of what we have already proved, that if we define a map psi from the collection of all equivalence classes of loops based at P0 in S1 to the set of integers given by psi of class alpha equal to degree alpha, then this map psi is an isomorphism. We first show that psi is a group homomorphism. Now, of course, this psi is well defined because we have already proved that whenever alpha and beta are two equivalent loops, they share the same degree. So, class alpha and class beta, if they are same, then their degrees are same. Now, let us come to the proof of that the psi is a group homomorphism. Let us take alpha and beta, two elements from pi 1 S1 P0. Since alpha is a loop based at P0, by path lifting property of exponential, we have a unique lift alpha tilde from I to R of the loop alpha, such that alpha tilde 0 is 0, exponential composed alpha tilde is alpha. Similarly, let us take the unique lift of beta as beta tilde. Now, we consider a path omega from I to R given by this expression that whenever t lies between 0 and half, omega t is alpha tilde 2t, and whenever t is between half and 1, omega t is described as alpha tilde 1 plus beta tilde 2t minus 1. Then if we put t equal to 0, we have the omega 0 equal to 0. Again, exponential composed omega evaluated at t is exponential composed alpha tilde in the first half of the interval, and in the second half of the interval it is exponential of alpha tilde 1 into exponential of beta tilde of 2t minus 1. Now, exponential composed alpha tilde is actually alpha, and alpha evaluated at 1 gives us the complex number 1. So, finally we have the expression for alpha star beta in the right side. Thus, W is a lift of alpha star beta starting from the point 0. Consequently, degree of alpha star beta is W of 1. The degree map is a homomorphism. If we start with psi of class alpha composed class beta, then that is psi of class of alpha star beta, but that is W of 1, which is alpha tilde 1 plus beta tilde 1, and that is psi of class alpha plus psi of class beta. The degree map is also a 1-1 map, because if we take any two elements from pi 1 S1 with the property that their images are same, then there are unique lifts alpha tilde and beta tilde of alpha and beta respectively, such that alpha tilde 0 is 0 and beta tilde 0 is 0. So, we define a homotopy capital H by using the straight line homotopy, that is HST is equal to 1 minus T alpha tilde S plus T times beta tilde S for any pair ST in the product I cross I. Then H is a path homotopy between alpha tilde and beta tilde. So, exponential composed H is a path homotopy between alpha and beta. This means that class alpha and class beta, they are equal. We also can show that the degree map is onto. So, we start with any integer n, we define a loop W from I to S1 by Wt is equal to exponential of nt, then the path defined by W tilde t is equal to nt lifts W, and W tilde 0 is 0. So, the image of class W is equal to the given integer n, proving that the map is onto. So, combining all these three, we have that psi is an isomorphism. We shall see now that if a topological space can be viewed as product of finitely many topological spaces, then the fundamental group of the topological space is isomorphic to the direct product of the fundamental groups of the component spaces. Now, we have already seen that the fundamental group of circle is the additive group Z, the group of integers. We shall utilize this fact to find the fundamental group of torus. So, the next theorem gives a method to determine the fundamental group of product of topological spaces. Suppose x and y are topological spaces and we fix 2 points x0 from capital X and y0 from capital Y. We shall show that the fundamental group of x product y with respect to the base point x0 y0 is isomorphic to the direct product of the fundamental groups pi 1 x x0 and pi 1 y y0. To prove this, we take a point class alpha from the fundamental group of x cross y based at x0 y0. This alpha is a loop based at x0 y0. So, P1 composed alpha is a loop based at x0 and P2 composed alpha is a loop based at y0, where this P1 and P2 are the corresponding projection maps. So, class P1 composed alpha is a member of pi 1 x x0 and class P2 composed alpha is a member of pi 1 y0. For the projection maps P1 and P2, there exist induced homomorphisms P1 sharp and P2 sharp between the corresponding fundamental groups. These induced homomorphisms are given by P1 sharp class alpha equal to P1 composed alpha class and P2 sharp class alpha equal to P2 composed alpha class. From the direct product of groups, we get a group homomorphism phi from the fundamental group of x cross y to the fundamental group pi 1 x cross the fundamental group pi 1 y, and that is given by phi of class alpha equal to the pair class P1 composed alpha comma class P2 composed alpha. We claim that this phi is a bijection. For this to be a bijection, we need to show that there exists another function, call it eta, in the reverse direction such that it becomes the inverse of phi. So, we define eta from pi 1 x cross pi 1 y to pi 1 x cross y by eta of the pair class alpha class beta equal to the class of alpha comma beta, where this alpha comma beta stands for the map from I to x cross y given by alpha comma beta at t is equal to the pair alpha t comma beta t. It is not hard to see that such a map eta is well defined. Also, eta composed phi evaluated at class alpha is equal to eta of class P1 composed alpha comma class P2 composed alpha, which is equal to class of the pair P1 composed alpha comma P2 composed alpha, but that is equal to the class alpha, because for any t this P1 composed alpha comma P2 composed alpha evaluated at t comes out to be equal to alpha t, phi composed eta of the class alpha comma class beta is equal to phi of class of alpha beta, which is equal to ultimately the pair class alpha comma class beta. Because for any t, P1 composed this map alpha comma beta evaluated at t comes out to be equal to alpha t, and similarly for the other one. Hence, phi and eta are inverse of each other, proving that phi is a bijection. As a corollary to this theorem, if we start with two path connected spaces x and y, then fundamental group of the product space x cross y is isomorphic to the direct product of the fundamental groups pi 1 x and pi 1 y. Now, it is known that a torus is homeomorphic to S1 cross S1. So, using the last corollary, we get the example that fundamental group of a torus is the direct sum of Z with itself. Now, since a torus is homeomorphic to S1 cross S1 and the fundamental group of S1 is known to be equal to Z, the cyclic group of integers, using the result, we get that the fundamental group of torus is Z direct sum Z. Now, just to mention that this is an example of a surface whose fundamental group is non-cyclic but abelian, and since it is abelian, we are using the notation of direct sum instead of direct product. So, we have constructed the fundamental group of circle and the fundamental group of a torus. In a subsequent module, we shall see how we can construct fundamental groups of several other surfaces.